Okay, so new topic for today. We are into chapter 6 now. This is the last chapter that we're going to cover. Recall, we're going straight through the book for a little while, and then we jumped up to chapter 9 for the purpose of connecting that linear algebra with the chapter 5 linear algebra, just to kind of get the whole linear algebra thing done. And now we're back to differential equations again. Just like earlier in the course where, we did a bunch of linear algebra, seemingly abstract, kind of where is this going? And then we saw, after quite a bit of linear algebra, we saw some tremendously powerful, very broad applications to solving a whole category of differential equations. Very broad and physically important category. So we've done some more linear algebra for a while now, and now with these linear algebra tools, we're going to solve another very broad, powerful category of differential equations. These are they are called systems of first-order linear differential equations. Like this. So systems because, well, there's a bunch of equations. This is not just a single equation. Right? First order, because there's only one derivative. Right? In each of these equations, there's no second derivatives anywhere, or any higher derivatives than that. Okay. And linear, well, you probably have a better idea now on why we're calling this linear. I'll make that precise in a couple minutes. But there's going to be a linear transformation underlying this kind of a system, and I'll write down exactly what that linear transformation is very soon. Okay. So here's the good news. We've already kind of seen the good news here. First order. Well, wow. We solved nth order equations back in chapter 4. This is only first order. Shouldn't this be a lot easier? Well, from a certain point of view, there is that. What makes these equations hard is the fact that they are systems. So this is not in different equations. This is a single system that includes the n equations. Now let me explain the difference. The point is you cannot just solve these equations one at a time. There's a temptation to say, well, how about I just solve this equation by itself? A couple of details, by the way. What are we specifically looking at? Our presumption in this question is that these functions here, what we call our coefficient functions, these are all given, and these g functions over here are all given. And what we would like to solve for are these functions y1 through yn. So again, our first temptation would be to say, well, let's just look at this equation by itself, and let's solve for y1. It's the first equation, let's solve it first, right? So here's the problem. There's a y1, here's a y1, but there's this great big unknown here. Yn. I haven't solved for yn yet. I can't solve for y1 if I don't know everything in the equation for y1. Right? This is a great big wildly unknown thing here. Okay, so you can't solve for y1 first. You'd need to know yn. Okay, so tempting then to say, all right, fine, I need yn. Great, let's solve for yn. Right? We'll solve for yn. There's yn, another yn in this equation for yn. Let's get to it. Well, problem. I don't know y1. Right? So you can't solve any one equation by itself until you've solved the other equations individually. And this is a vicious circle. This is not a strategy that has any reasonable chance of succeeding. Okay. So that's what makes this hard. The fact that we have a linked system. Your y2s are in my y1 equation. Your y3s are in my yn equation. Each equation is wrapped up in each other equation, and you have this nasty rat's nest of connections between the various functions that you're looking for. And as a whole, it's a hard problem. Okay. Alrighty. So, a little bit of notation. How we're going to address this. Let's take all these coefficient functions. Let's call them a matrix A. So this is a matrix valued function, or you might say a matrix of functions. Let's take these G's over here that are on the right-hand side, if you will. Let's call those this G vector of functions. Notice that we are trying to solve for this list of unknowns, y1 through yn. Let's call that a vector. And notice if you make these choices, this is just an observation, if you choose to organize these various givens and these various unknowns exactly in this way, well, a wonderful thing happens, and that is that this entire monstrosity, that entire system of equations, you can rewrite like this. This y vector, its derivative, is itself times your coefficient matrix A plus this G vector. So you can rewrite the whole system as a single, I'm going to say a single equation. Now, okay, but there is something new about this kind of an equation, right? This is a differential equation. There's a derivative, there's an equal sign. This is a differential equation. But this is a vector-valued differential equation, right? With a coefficient matrix. This is not something we've seen before. This is a new thing. Again, this is really just notation, of course, for what we have up. Okay, how are we doing? Is everybody on board? See what we're up against? Okay. Okay. A little bit of terminology. If G, this thing here, if that's 0, we call it a homogeneous system. Y'all probably remember that whole business about homogeneous in chapter 4. Homogeneous meant G equals 0. So here's something we're calling G. If it's 0, we call it homogeneous. Now, quibble, in chapter 4, the G was the right-hand side of the equation. That's not the case here. This G is not the right-hand side of the equation. So is this really analogous? Let me point out, though, that equation is the same as this equation. And now, G is the right-hand side of this equation, right? So it's just a question of how you write it. A very reasonable question that you might ask at this point is, all right, well then why didn't we write it this way in the first place? I mean, if we're thinking of G as being, in the analogy to chapter 4, kind of like our old right-hand side, why write it like this? For one thing, it doesn't matter. For another thing, while there is a point of view that makes this a really nice way to write down the equation sometimes, there is a different point of view that makes this a really nice way to write down the equation sometimes. So we're going to be using both points of view, importantly, in different ways and different circumstances. Okay. All right. Another little bit of terminology that we kind of have to get out of the way. Recall that in chapter 4 we talked about this thing called an initial value problem, which was a differential equation combined with initial values, right? So initial value problem. So same thing here. If you add in some initial values, such as this, at some input point x naught, some starting value of x, you require that this vector valued function take these specific values, those are called initial values, and combine with the differential equation as an initial value problem. Okay. All right. So, by the way, you may have noticed certain analogies between what we're looking at here and what we saw in chapter 4. The terminologies kind of track. The whole idea of a right-hand side, you look at it from the right point of view, that kind of tracks. Coefficient equations, a lot of this stuff kind of tracks. We're going to see tremendous analogies between what I'm going to loosely call chapter 6 differential equations like these and chapter 4 differential equations, from earlier in the course, linear differential equations. We, of course, paid particular attention to the constant coefficient linear differential equations. Okay, next big step in that analogy. This theorem is the chapter 6 analog of one of the first things that we wrote down in chapter 4. Back in chapter 4, one of the first things we wrote down was our existence and uniqueness theorem. Right? We needed our existence and uniqueness theorem to shelter us from the horrors of anomalous, weird things that can happen if you don't, make certain nice assumptions about the nature of the differential equation. We saw some terrifying things that you could have an initial value problem that actually has not only more than one solution, but infinitely many solutions. And depending on what kind of little oddities you write down, you can find differential equations that, for some initial values, have infinitely many solutions. For other initial values, have no solutions. All sorts of annoying, inconsistent, difficult things to deal with. Okay, but we wrote down an existence and uniqueness theorem that says that if certain nice conditions are satisfied, then it works out just like you would want every time. There's always exactly one solution. So here's the chapter 6 analog. If those coefficient functions and your, what I like to call right-hand side functions, are all continuous. We're not going to prove this theorem because, beyond what we can do in this course. But if those functions are all continuous, then the initial value problem, keep in mind an initial value problem is a differential equation combined with an initial condition. The initial value problem not only has solutions, but that solution will always be unique. So again, this is what I like to call an existence and uniqueness theorem. The solution exists, and the solution's unique. So again, we need this to protect us from the jungle of horrors that might occur without making these assumptions. Under the umbrella of this theorem, everything works out just like you would hope. Okay. Alrighty. Okay, so now we've been talking about a lot of what you might call analysis, a lot of calculus. We've been talking about derivatives, and we've been talking about functions. Looking for this, what is the function? What is this list of functions whose derivatives satisfy these equations? It sounds like calculus kind of stuff, which, in the broad category we call analysis. So it looks like an analysis problem. Let me remind you, in chapter 4, one of the big points, right? One of the top couple, top 10 takeaways from Math 216 was this very broad category of differential equations in chapter 4 are fundamentally not really analysis problems. They are fundamentally linear algebra problems. That's one of the big takeaways that I want you to leave this course with. I claim really the same thing is going on here in chapter 6. So just to start to lay the groundwork for that. Here's your differential equation, sure, but let's talk about what are these solutions. Well, a solution, it's not just one function. A solution is a list of functions, y1 through yn. It's an ordered list of things. It's an ordered n-tuple. Oh, okay, of functions. Yeah, sure, right. But it's an ordered list of things. And in fact, seeing as it's an ordered list, right, then we can think of this as being something in the same sense that an ordered list of reals is Rn, a vector in Rn. Likewise, an ordered list of functions in a certain category, I claim that these functions are all C1. An ordered list of C1 functions is, you can think of it as an element of this thing called C1n. And the big point that I want you all to think about, and I want you to check for yourself, this is not hard to do, but the collection here that I have written, the collection of all ordered n-tuples of functions from the vector space C1, this ordered n-tuple of vectors, this is a vector space. So we are doing business inside of a vector space. Right there, that means we're doing linear algebra. Kind of, at least kind of. Okay, so we're trying to find something inside of a vector space. Now, here's the next thing. From an analysis point of view, we're looking at, solutions to a system of equations. Okay, fine, sure, but let's look at it this way. We are looking to know when that happens. Therefore, we are looking to know when that happens. These are the same equation. Right, I mean, move the thing over to the left or the right, whatever, that's their, equivalent. We're looking to know when this thing is equal to 0. You can check for yourself. This is another fantastic exercise. Everyone should do this. This is a linear transformation. So, yeah, we're looking for functions whose derivatives satisfy equations. Yeah, sure. But said differently, we are looking at a linear transformation on a vector space, and we want to find the kernel. Where is that linear transformation equal to 0? We're trying to find the kernel of that linear transformation, which of course we also know from way back is a subspace. Right, so that's a lot of linear algebra talk. We're looking for the subspace that is the kernel of a linear transformation acting on a vector space. It is very much a linear algebra problem. Okay, so keep that in mind as we go along. Now here's the analogy continues. One of the first things we wrote down back in chapter 4 was that the set of solutions is a subspace of dimension n. Y'all remember this result? This was a big deal. Reminder, how did we use this back in chapter 4? We used this to actually to put a pin in our solutions, right? Certain calculus observations and clever sort of trickery about characteristic polynomials allowed us to find some solutions. We found a bunch of solutions. And how do I know that there aren't more solutions, right? Well, I had to make linear algebra arguments. I had to say, look, I know there's an n-dimensional space of solutions. I have found, look at this, I have found n solutions that are linearly independent in this n-dimensional vector space, and therefore by a dimension argument, we argue that we have actually found all of the solutions. Dimension was key in being able to make that argument that we have in fact finished, that we found all of them, right? So here's that analogous theorem. Good news if you have one of these systems, by which, by the way, I mean that this matrix is an n by n matrix, right? Then our set of solutions is n-dimensional. Okay. All right, so just like in chapter 4. So like I say, the analogy continues. All right. Now, I would like for y'all to prove this theorem. I'm going to show you how to do it, but I want y'all to fill in the blanks. I think you can do this. We're going to prove this theorem. You are going to prove this theorem by stealing pretty much all of the ideas from how we proved this theorem that came from chapter 4. We did it, though, in chapter 5. We set up a linear transformation from the vector space of solutions into the vector space of initial conditions. Right, this linear transformation is plug in x equals 0. Real easy linear transformation. Real easy to check that it's a linear transformation. Let me write that down. So this is a linear transformation. You then argue that this linear transformation here is a bijection. You argue that it's a bijection by way of the existence and uniqueness theorem. Right? That's what the existence and uniqueness theorem says, that for every initial condition, there is exactly one corresponding solution. That makes this a bijection. And then you refer to an old linear algebra result. If you have a bijective linear transformation, which we do, between two vector spaces, which we do, then the dimensions are the same. Task for you guys. think about what does this vector space of initial conditions look like? What dimension is it? You're going to find that it's n-dimensional. Therefore, our vector space of solutions is n-dimensional. Right? So it's a very analogous, it's a really, really strong analogy to how we proved the result back in, we proved the chapter 4 result in chapter 5. That same exact method will prove this result here. So give that a try. There's a lot of blanks to fill in. I've deliberately left you some blanks to fill in. Try to fill in those blanks. Okay. All right. This would be a great question to ask in discussion section next week if you have trouble with it. Of course, you're also welcome in my office hours, the TA office hours. Any of those are fine. Okay. We're looking at a subspace. We're looking at so therefore a vector space is our object of interest, this collection of all solutions. A basis for that subspace we call a fundamental set of solutions, just like we did in chapter 4. The analogy is extremely strong. Something that we couldn't do back in chapter 4, but we can do here, keep in mind that each one of these solutions is in fact a vector, right? A solution is a list of functions y1 through yn. So if I have a bunch of those solutions, each one individually is a vector, right? I can then sort of assemble those vectors, et cetera, et cetera, et cetera, and make a matrix of functions like this. Be real careful, please, on the indices. It's really easy to get this wrong. It's easy to think of, okay, well, we've got y1 through yn. We've used the subscript to indicate which of the functions inside of a given vector-valued solution. But now we're also using an index, differently, to distinguish different vector-valued solutions from each other. So we're using indices in two different ways. When you write down this matrix, there are two different indices here. Just heads up, be careful. Make sure you're using them the right way. Okay. Now, why would you want to do this? What's the point of taking a basis, namely a list of vectors, and writing it as a matrix? Maybe this isn't that surprising. There have been plenty of circumstances in the past where a bunch of vectors assembled into a matrix was handy for one reason or another. Right? Now, does that mean automatically that it's going to be meaningful and handy here? No, certainly not. But it is. And exactly how this is useful, we're going to see in a few minutes. Okay. All right. Oh, hey, that reminds me. I'm sorry. I forgot to go back and connect something up. I forgot. I was going to try to explain, why is this what we call an initial value? How come you only look at the values? Back in chapter 4, we looked not just at the values of the solution, but we also looked at a bunch of derivatives. Why aren't we looking at a bunch of derivatives here? Short answer, the reason why is because this is the notion of an initial condition that makes this theorem work. That makes it that you have solutions and that those solutions are unique. If you were to fiddle with this definition of if you were to define an initial condition to be more information than this, you would no longer have a guarantee that solutions would always exist. And that's just how the reality of the matter works out. If you were to make this weaker than it is, in other words, for example, maybe you make an initial value just the values of some of the unknown functions, then your solutions would not be unique. Right? So exactly this notion of initial condition, we choose this to be what we call an initial condition because that is what makes it work out so nicely that we always have exactly one solution to the equation. Okay, I just wanted to link that back up. Okay, so let's get our hands dirty. Let me remind you what we were looking at. We were looking at these kinds of equations, right? We've got this great big bunch of equations here, in different equations, in different unknowns. We are looking for a solution, by which we mean a bunch of functions, an ordered list of functions, a vector of functions. Okay. So here's an explicit example. Whoops, I want to do that in blue. This system right here, that is a first-order linear system of differential equations. And let me explicitly write that out for you, just to remember what we're talking about. Is actually a system. So this says y1 prime equals 1y1 minus 3y2, and y2 prime is negative 2y1 plus 2y2. So I didn't mean to put a vector. There we go. Okay. So that matrix equation is equivalent to this system. Everybody on board? You can see the appeal. Right? This is a more compact way to write it down. Okay. At this point, going forward, most of the time I'll write it like this. But heads up, make sure you are also aware of what we're really doing. This is what we're really doing here. Okay, so I don't know if y'all remember. For I'm going to say dramatic purposes. How I, at this stage in Chapter 4, when we were looking at our very first actual nth order constant coefficient equation, how did I do the first solution? Back in section 4.1, not even the 4.2 yet. What I did is I pulled a couple of solutions out of thin air. And then I made a bunch of linear algebra arguments, right, to show that, in fact, those are all of the solutions. It was kind of like a magic trick. I didn't solve. I never took any anti-derivatives anywhere in that process. I just said, oh, hey, check this out. That works. Oh, would you look at there? That also works. Linear algebra, linear algebra, linear algebra. We are done. There are no more solutions. Right? So I kind of like coming at it from that point of view. I mean, again, the big takeaway I want you to get here is not how do you find the solutions. That's not the takeaway. The big takeaway here is linear algebra is the thing that solves the differential equations. This is fundamentally a linear algebra question. Linear algebra tools that make the argument go through. So that's what I want to do here. Again, I'm going to pull a couple of solutions out of thin air. I'm not going to show you how I got them yet. Of course, obviously, we'll get to that very soon. For the moment, though, let's not worry about where these solutions come from. Let me just abracadabra. This is a solution to that differential equation. If you plug that in there, take its derivative. If you plug it in there, multiply by that matrix, compute both sides, that works. If you prefer. If you were to take these functions and plug them into there and into there, the system works. Everybody should do this once in their lives. It's really easy calculus. It's a derivative, a little quick matrix product, right? Nothing to it. But, pull out a pen and actually crank out both sides and confirm for yourself that, wow, look at that. That actually works. So please take the 30 seconds that it'll take you, at some point and confirm that that works. Okay. Okay, and here's the other one. This also works. You plug it in there and there. Compute, check. Likewise for the, if you break it down by coefficients also, check. Okay. All right. And pretty much we're done with the calculus at this point. Everything on here on out is linear algebra. So how do we proceed? Well, let's see here. This is a 2x2 matrix. Therefore, our theorem tells us that we are looking for a two-dimensional vector space. Right? We're looking for a two-dimensional vector space. I have found two vectors in our two-dimensional vector space. Casual inspection, they're clearly not parallel. Therefore, they are independent. I have an independent pair of vectors in a two-dimensional vector space, and a dimension theorem tells me that therefore they are a basis. And therefore, the complete set of solutions is simply the span of those two, those two rabbits I pulled out of a hat. Or if you prefer, said differently, you could just say these two solutions that I found are a fundamental set of solutions. The implication of which then is that all the other solutions are in the span of that independent pair. And we're done. So note how linear algebra is what allowed us to really proceed. Once we had this and this, if we didn't know any linear algebra, it's like, well, wow, that's a hard problem. I seem to have stumbled across two solutions. I, however, don't know if there are more. And if I were to find more, I wouldn't know if I was done. And I don't know where to go from here. Right? You take away the linear algebra, and we don't know hardly anything at all. Linear algebra answers the question. Everybody on board? Okay. All right. Okay, so last thing I'll observe here real quick, and this is just kind of notationally cute, I guess you might say. But if you look at this general solution there, observe that general solution is this product. This is why what we call that fundamental solution matrix. This is why that fundamental solution matrix is cool. That bigger, more complicated expression is just fundamental solution matrix times a vector of constants C1, C2. Multiply it out, right? I mean, take this matrix, multiply by this vector C. That is, we're taking the C1, C2 linear combination of the columns of this matrix. Again, that's how matrix multiplication works, linear combinations of the columns. Well, the columns are the things that you see up there I want to take linear combinations of. So it's an immediate connection there. So anyway, it's kind of nice, I guess. It's not importantly a big deal to be able to do this, but nevertheless, it's kind of nice. Okay, let me take a pause real quick. Does anybody have any questions so far? Okay, everybody's happy. One thing you could do, if you want to kind of, predict where does the lecture go next, you could just go back to chapter 4 and say, well, what's the next thing we did in chapter 4? Right? The analogy continues to be very strong. The next thing we did in chapter 4 was to talk about particular solutions and homogeneous solutions and general solutions. And there was that theorem back in chapter 4 about how particular plus homogeneous gives you general. The analogy continues. That is also true here. If you have a fundamental set of solutions to the homogeneous equation, and then if you add to that a particular solution to a non-homogeneous equation, that sum gives you the general solution to that non-homogeneous equation. Sound familiar? Right? We wrote down word for word exactly that same theorem back in chapter 4. Which, by the way, at the time, you might recall, I observed, hey, this is exactly the same result, word for word, as a similar theorem that we saw back in chapter 1. Right? That particular plus homogeneous gives you general. For matrix equations, right? We had talked about systems of linear equations way back in chapter 1. But then in chapter 5, I made the observation that, look, coincidences, seeming coincidences like this, very often are indicative of deeper truths, right? And what I suggested in chapter 5 was that you state and prove a generalization of all of these, and that is that if you have any linear transformation, right, from a vector space V into any vector space W, for any linear transformation, you can write down very reasonably what would it mean to talk about a homogeneous equation. What would it mean to talk about a non-homogeneous equation? What would it mean to have a particular solution and homogeneous solutions? And in fact, in that, write down those reasonable definitions exactly as you think they should be. And there is a theorem that says particular plus homogeneous equals general. Right. So again, we went through the details of this back in chapter 5. So I hope you might have given some thought to writing down those details, filling in those blanks, stating and proving that theorem. Here, I will just say this is a special case of that general theorem. So no surprise that the pattern continues. Okay, nice exercise. I hope you'll all give it a try. Okay. All right. Where's my? Here it is. Okay. All right. The Ronskian. Again, this is next thing that happened in chapter 4. The analogy is very strong. Okay, so the Ronskian. There's a lot to say about the Ronskian here in this chapter 6 context. In fact, I want to talk even more about a more general sort of adaptation of the Ronskian. The Ronskian that we talked about in chapter 4 was actually. I guess this was chapter 2. Yeah, it was chapter 2. But then we modified it in chapter 4. Here's the thing: it was very limited in scope. The Ronskian applied only to functions. That's it. If you have a list of functions of certain regularity, you need them to be n times differential or n minus 1 times differential. If you have a list of functions, then you can go through a very narrow process. Take each function, start taking derivatives specifically, assemble those derivatives in a certain way to make a matrix, take that determinant, and this expression is this magic trick called the Ronskian, which has certain properties, and if it's non-zero, then that tells you, et cetera, et cetera. Okay. So, very narrow application, only two functions. I'm going to show you a more general construction. This is not in the book. Suppose you have a list of vectors in any vector space, and I emphasize any vector space. I don't care. Whatever. So this does not have to be a list of functions anymore. It could be a list of matrices. It could be a list of images. If you think of images as being vectors in a vector space. Whatever. And let's ask the same question that we asked when we were talking about the Ronskian. How do you decide if they're independent or dependent? So clever argument that you can make. Here it goes. First observation is to point out an easy result about linear dependence. If your existing list, if that were dependent, then the images are always dependent under a linear transformation. This is an easy little theorem to prove. Not clear why we care yet. This is an easy theorem to prove. Let me tell you how to prove this. Again, details for y'all. This is a brute force. It's not even that brute. This is a gentle force, gentle application of force theorem. Suppose that you have a dependent list of vectors. Okay, that means you have a relation. Write down the relation. Take that relation, apply the linear transformation, and use linearity. And what comes out immediately after your application of the linearity, what you end up with is an explicit relation among these image output vectors. And therefore, this list is dependent. So, really easy to prove. Again, good exercise. I hope you all will give that a try. Ask me in office hours, discussion section for the TAs, whatever. So what? This doesn't answer our question. Keep in mind, I'm trying to decide about these vectors. This is what I don't know. This theorem, as I have it written down, has the awkward feature that it assumes I know the answer to the question I'm looking for, which, of course, that's not helpful. Okay. All right, so here's how that's useful. I hope you all remember this construction called the contrapositive. I use this a lot, right? It's very useful in lots of situations in math. The contrapositive of this implication is this implication here. Our starting statement, dependent inputs gives you dependent outputs. The contrapositive says independent outputs must have come from independent inputs. Logically equivalent, these two statements. Right? So take a moment, make sure you're comfortable with this equivalence. And here's where this pays off. Keep in mind, I've got a list of vectors. I'm trying to decide if they're independent or dependent. Nay, check it out. Now I have an answer to that question. I have a theorem that says, hey, certain conditions, if you check certain conditions, you get to conclude an answer to the question you were looking for. Right? Well, okay, so let's try to figure out then, what are these conditions? How might I decide if these outputs are independent? Well, don't forget where these outputs live. This linear transformation that we started with, we were assuming that these are Euclidean. This is a Euclidean valued linear transformation. These are vectors in Rn. I have here a list of n vectors in Rn. This is a chapter 1 condition. N vectors in Rn are independent. Oh, I guess it's chapter 2. But n vectors in Rn are independent if when you assemble them like this and take the determinant, you get non-zero. Okay, so there's your theorem. A very powerful theorem. This Euclidean valued linear transformation, right? Euclidean valued linear transformation, like so, allows you to define this construction, this, what I'm going to call a Ronskian-like construction. Let me just leave that hanging for a moment. But this construction has the amazing feature that non-zero implies independent. And gosh, doesn't that sound familiar? Doesn't that sound just like the result we had back in chapter 2, right? The very first time we wrote down the Ronskian, we were looking at, it was a list of functions, and we took some derivatives, blah, 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 and ended up with, hey, this thing, if it's non-zero, we get to conclude independence. That's exactly what we have here as well, right? So, that's why we call this a Ronskian-like construction, because the theorem is structured just like our old Ronskian theorem. How we doing? Everybody happy? On board? Let me emphasize how much more powerful this is than what we did back in chapter 2. Back in chapter 2, it was strictly only a vector space of functions, and furthermore, pretty nice functions, that highly differentiable functions. That was it. This now applies to any vector space. Furthermore, that whole business back in chapter 2, where the way you structure your Ronskian is you write those functions down, and then you, strictly speaking, you take derivatives. Only derivatives, just derivatives. Nope, here, any linear transformation. Any linear transformation, it's got to be Euclidean valued, right? But any linear transformation, any vector-valued linear transformation, and throw it together in this way, you've got yourself a Ronskian. You've got yourself a way of deciding on independence. So, very, very powerful idea. Here we, you might say, in chapter 2, what we, let me do it like this. In chapter 2, we were using this as our linear transformation. Take this linear transformation, apply as above, and that gives you the old classic Ronskian. Okay. All right. So what we're going to do in our new circumstance. Now keep in mind, why are we considering all of this? At this point, we are looking at, where are we? Here we go. We're looking at vector-valued functions. What I need to do now is figure out how to take these vector-valued functions. How do I take vector-valued functions, and what might I do? We have to contemplate, what might I do to a bunch of vectors to turn them into vectors? Right? That's my only requirement. I have to have vector-valued outputs. What can I do to a vector to give a vector? How about this? How about we don't do anything? Right? Let's just leave it there. The action of doing nothing, remember, is a linear transformation. So the identity transformation is what we plug in to create our new Ronskian of vector-valued functions. And here it is. You just take these vector-valued functions, just assemble them. Don't take any derivatives at all. Just assemble them. That makes a matrix whose determinant is our Ronskian. Special case of our generalization on the previous page. Let me take a moment again to let me breathe, and y'all decide if you want to ask a question. Anybody? How we doing? Free. Okay. Good news. This Ronskian is pretty much just as powerful as the chapter 2 Ronskian that we used a lot in chapter 4. So here you go. If the Ronskian is identically 0, you get dependent. If the Ronskian is never 0, then you get independent. Right? This is just like our our chapter 4 Ronskian, just like our chapter 4 Ronskian, namely, if you're looking at solutions to our special kind of differential equation, then it lines up in this perfect way. Not only does non-zero mean independent, but 0 means dependent. Just like we saw in chapter 4. Easy example. Remember, we were looking at this differential equation previously. Right, wrote down a couple of solutions. Now, the solutions. I already know they're independent. It's easy to look at these two vectors and see that they're independent. Don't forget, 2 is a wonderful number. Right? All sorts of good things happen in 2 dimensions. 2 dimensions makes it really easy to decide on independence. Well, either they're parallel or they're not parallel. It's the only possibilities, and it's all we really care about. So these are not parallel, therefore independent. So we already know that they're independent, but look how the Ronskian behaves correctly. The Ronskian is never 0. So we correctly conclude what we already knew in the first place in this case, but we correctly conclude that that list is independent. Okay. How we doing? Everybody happy? Okay, last thing I want to do real quick. This is the last topic I want to hit here, but this argument here, I emphasize that this applies for any linear transformation, any vector-valued linear transformation. I have some old exam questions that capitalize on this. Let me explain what those old exam questions did. In those you'll find them when you're looking through my old exams. In those old exams, I gave you a bunch of values associated with some functions, just kind of semi-random seeming information. Like, we've got these several functions here. Here's all of their integrals from 0 to 3. There's all the values for these functions, and here's all of their second derivative evaluated at x equals 5 minus their first derivative evaluated at x equals 0. I'll give you those values for all the functions. I gave you a bunch of random information about a list of functions. And the insight to make in all of these old exam questions is, hey, these are not just random information. Each one of these values is a linear transformation. So the point is, all students have to do for these old exam questions is just take the given information and assemble them into a vector-valued linear transformation, with which they then can create their own Ronskian. You can make your own Ronskian, right? With which you can then, compute the value, see if it's non-zero, and conclude independence, just like in chapter 2. So take a look at those old exam questions. I think you'll find that they fit this pattern very nicely, and this makes for a good stopping point. Y'all have a good weekend. See you on Monday.